Good morning, grade 12s. Well, listen, I'm going to talk to you about some, just, finishing off that quantum unit today. And guys, listen, before I start, I just want to tell you that, like, I get it. I get how you feel right now about finishing off the school year. It's always hard in June, even under normal circumstances. But under these circumstances, with a pandemic and everything else, um, yeah, I get it. Like, I am sick of it too. I would like it to be finished. I'd like it to be over. Especially with my grade 9 class. Like, I'm kind of done with that. And it's been very frustrating, I have to say, this distance learning thing. I get it. I get how you feel. I get how you want it to be over and everything. But, at the same time, like, I really feel compelled and I really feel it's important to finish the task that we started in the time we have remaining and not just blow it off because it's because we're sick of it. I think that's not the right thing to do. Um, and so I want to finish this thing. It's too bad. I really enjoy this unit. I really enjoy the quantum thing. There's not a lot of difficult math in it or anything like that. It's actually pretty straightforward. There's some cool things about it. So anyway, I'm gonna do it. Like, I mean, you might be of a different mind. Like, I've heard from people in your class, 2, 3 weeks ago saying, you know what, I'm not feeling great right now. Maybe I'll blow off the rest of the month. You know what I mean? And I just know that, like, if it weren't for the pandemic, we would never have that conversation, and no one would ever say that to me, right? Like, for me to to listen to someone tell me that as a teacher is a very difficult thing for me to hear. I feel bad for you. They're just throwing in the towel, like some of you. Um, yeah, I don't know what your situation is. I don't know what's going on at home or anything else. I know what it is for me and my boys and myself. And, we're sitting here and there's honestly not a lot to do. And maybe we don't feel like doing schoolwork, but you know what? It's a good thing to be doing, I think. Um, anyway, I'm not going to say anything else about it. I just like, I care about your education. I think you should too. I think you should just persevere these last couple of days and, one more lesson, one more practice test or whatever, one more test, and not sort of like blow it off like, well, you know what, it's at the end. Now you have the option. You have the option to do that. Like, you can get your pre-pandemic, but, like, I mean, I have to do what I have to do. So if you're gonna not do the last test or whatever, I'll put the mark as a 0 or whatever. Okay, I have to do that. And then I'll just look at your marks, and whatever is better, the pre-pandemic, like the pre-school closure in March, or the present mark, and I'll just give you that on the final, as a final report card. Okay, mark. And that's basically it. Most of your marks have gone up during the pandemic. So anyway, I hope you don't throw it away on this unit. It's not a difficult unit, guys, like, seriously. Anyway, okay, with that in mind, I'm going to now show you, like, I love this lesson. It's so strange, guys, and so cool. I actually have a video for you. I'm not sure how well this is going to work. I'm going to try it here, and I'm hoping you can hear the sound, and I'm going to actually play this video. It's a 5-minute video, but I'm going to pause it sort of at different times. It's the famous double slit experiment. Some of you may have seen it before. Okay. Richard Feynman once said that all the weirdness in quantum physics, and trust me, it's weird and spooky and bizarre, okay? But it's real physics, right? But all the weird stuff you can think of if you just want to consider for a moment the double slit experiment. Now, there's weird stuff happening all over in quantum physics, but the double slit experiment sort of encapsulates it all really well. All right, so I'm going to play this, and I'm going to stop it from time to time. All right, so what you saw there was what happens when you shoot particles through slits, okay? And you make sense. You get a sort of pile of particles showing up on the screen behind where the hole is, okay? Which makes sense, right? You're firing stuff through a hole. You're going to see those particles accumulating behind the hole, okay? So if there are two holes, you'll see two piles. Makes sense.
Let's look at waves. The wave, the slit, and radiating out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity.
Here they should show the single slit interference pattern. They didn't show it, but whatever, we'll let it pass. Okay, one wave can produce interference, like one slit can produce interference too. We've seen that ourselves. But anyway, it doesn't really matter. Okay, let's get back to it.
This is similar to the line the panels make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things that is matter through two slits, we get this, two victims of things. And with waves, we get an interference pattern of anything. Good so far. Now, let's go quantum mechanics. It's a tiny, tiny bit of matter, like a tiny marble. Let's fire a screen through one slit. Immediately, just like the marble, a single beam.
Okay, now actually here, if you were to fire electrons through a single slit, they would actually produce a single slit pattern, okay? But it would be difficult to measure it. Like, so electrons have very, very short wavelengths. They shouldn't have any wavelengths at all, okay? The fact that I could measure the wavelength of something like an electron where there is no wave, like it's not an electromagnetic disturbance, so we can't even understand it as a wave like that, okay? That is what's so strange about this.
So, if we shoot these tiny bits through two slits, we should get, like a marble, two patterns. What? An interference pattern. We fire electrons. Tiny bits of matter. We get a pattern like waves. Not like a marble. How do pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern.
So just to explain what he said there, he said maybe the beam itself has some type of wave-like interference between the particles, like in the beam. Almost like, imagine like a beam of water molecules like out of a super soaker, but there's a wave in the beam and at the same time it's a stream of particles. So that was the suggestion. So then they're going to show you here, if you fire the electrons one at a time, okay, then you should destroy the interference pattern. Okay, so like he went through a few possibilities there. In fact, there's an infinite number of possibilities. Okay, like there are so many different paths that object could take on the way to that screen. Okay, and all of those things mathematically exist in superposition with each other. It's the only way to explain the interference, which makes no sense. Okay, it's like me saying the electron is everywhere at once, like not just in one place, but everywhere, all at the same time.
All of these possibilities are consolidations with each other. But physicists were completely baffled by this. So they decided to investigate and see which slit actually goes through. They brought a measuring device by one slit to see which one went through, then let it flow. But they were let to flow as far upstairs than they could have imagined. When they observed, the electron went back to behaving like normal. It produced a pattern of two phases, not an interference pattern.
So if you observe it, no interference. It goes away. Okay, and that is very strange.
The very act of measuring leads you to observe which slit it went through meant it only went through one, not both. The electron decided to act differently. As though it was aware it was being watched. And it was here that physicists stepped forever into a strange, never heard of quantum physics. What is matter? Particles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the way it functions by observing.
So there you go, guys. That sort of summarizes it. There's a few little mistakes in there, and it's not perfect. Okay, that video, but something really strange is going on here. In fact, I watched. There was a research project that's been done over 8 years, where they've asked people, okay, to sit next to a laser that's doing the double slit experiment, and like in extremely tightly controlled conditions, like in an optical table which doesn't vibrate or anything like that. And so what they're asked to do is imagine that they can see which slits the photons are passing through. And what they do is while they're concentrating, they can't actually see the experiment happening at all. It's all happening inside a closed tube, but they're asked to imagine it. And then they're asked to concentrate and imagine that they know which slit the photons are going through, okay? And by simply knowing it, will they be able to affect the interference pattern, okay? And so what they did, and this would be extremely bizarre because they're not actually observing it, they're just observing it in their mind's eye with their conscious sort of mind, right? But not actually observing it, only imagining it, okay? And when they did the experiment, and like it's been repeated many times over 8 years, okay, by different people and everything. They even did it online, so you could log in and try to affect the laser beam experiment with your mind from a distance, like from halfway around the world, okay? Anyway, they did the experiment, and they had extremely statistically significant results. What happened was the intensity, the interference pattern stayed there, but the intensity of it reduced when people were concentrating on it, okay? Almost as if their conscious mind somehow affecting these quantum events, okay? And it's action at a distance that's happening outside your brain, okay? So, and people who could concentrate, like people who are meditators who have a really strong ability to concentrate and focus, they had even greater effect on the experiment, where people who are easily distracted or whatever can only concentrate for a few seconds sometimes did not have a positive result. But it's kind of cool how that worked. And how do you explain it? I mean, the results from the scientists range from like, oh my God, like what is this? To something like disbelief, like saying something must be wrong here. But they've gone through every possible alternative explanation and come up with nothing. So anyway, double slit experiment, very famous experiment in physics, and you can find all kinds of weird things about it online. But yeah, that's it's weird, okay? And I just want to go through a couple things. There's not a lot of equations or anything today that you have to know for a test. It's just notes, so I'm just going to go through it quickly. All right, so like how do we marry these two concepts of waves and particles together? Okay, well, actually, before I look at these notes, I just want to show you um, different ways that we think about it. So I have in the original photo, or sorry, in the original history, pardon me, in the note I gave you the other day, this photo here, okay? So here's the deal. Here's a double slit experiment that they were talking about in that video. And if you fire one electron at a time so that the interference cannot happen between electrons in the beam, if there's only one going through at a time, they land on the screen and form dots. And then over time, you see the interference pattern appearing, right? And this seems completely impossible because the electron itself is way smaller than the slits, and it does not span the slits. It cannot possibly pass through both slits at the same time. And yet, we know that the spacing of the bars is affected by D, the distance between the slits, okay, and it's also affected by W, which is the width of the slits, and you know, it's also affected by how many slits you have, and so like these spacings, like where they land, seems to be they're disturbed. Like if logic just says that an electron has to go through either one or the other, right? Then how could it possibly know where to land, right? Having not gone through the other slit at a certain distance away that will determine where these nodes and antinodes are. Okay, so anyway, it's really strange, but one way that the way we sort of settle it today, it's not settled. We can't answer the question. It hasn't been answered, so I want to make that clear right away. But we just say, look, we have wave equations that we studied in the wave unit on light that will tell us, okay, the spacing of these nodes and antinodes. So we'll just use those equations, okay, when necessary to describe an interference experiment, right? And so the wave equations will tell us the probability of where the particles will land. So sometimes we call them probability waves, okay? So, you know, let's say you're looking at orbitals and atoms, the 1s orbital, it looks like you see a picture of it, okay? That picture is telling you the probability of where you can find the electron. So the p orbitals look like dumbbells. They look like something like this. Okay, let's say px, py, and pz. So there's a node in the middle, so you'll never find the electron there. It's always going to be somewhere over here or somewhere over there. Okay, now it's only one electron. Okay, there could be two in the orbital, but whatever. Whether there's one or two, they form like, we call them like clouds. Okay, it's the weird thing about it. Okay, where you find high probability of finding the electron either here or here, but a zero probability of finding it there. Okay, so that's where there's a node. Where the antinodes are, you'll find high probability. But the electron's just a dot. It's just a little guy. What the heck is this wave? Like, what's the node and antinode in that p orbital? Well, we don't really know. We just know that when the electron is confined around the atom, it behaves like a wave like this. And its location is uncertain. It's somewhere in here, but we don't mean uncertain like we're just not sure where it is. That's not what we mean by uncertain. We mean it's actually everywhere. It occupies this entire space. One electron occupies both of those clouds. Okay, it's not just that it's somewhere in here. It's just when you're not peeking and looking at it, it's everywhere in here, all at the same time. And then when you peek and look, it'll show up in one spot. And the odds of finding it are given by this shape that you see here, of where you might find it. Okay, but that's actually completely random where you might find it. You might peek the first time and find, I'll use a different color. The first time you peek, you find it here. Okay, right there. Then the second time you peek, it's over here. Okay. Now you're probably thinking it moved, like it maybe took some kind of path and moved over there. But the thing is, when electrons move, they release electromagnetic energy. Okay, we know that from the wave model. Okay, so a moving electron will release electromagnetic energy, but the atom never did that, right? So how did it get there? If it moves along any path you can imagine, it will release light when it does that. But it's no longer in the same position. It's now moved from the blue spot to the red spot. But how did it get there without releasing any radiation? Because when it moves, it always releases radiation, but it didn't. So the only explanation is that it teleported. So it's like teleportation, like science fiction we're talking here, right? It seems to teleport all around that cloud, right? But that makes no sense. How does that even work, right? Teleportation. That seems to do that. It moves without moving, okay? Like if you could sit in your chair, blink your eyes, and then you're sitting in another chair in another building in some other place in the world, you moved without moving. Like you didn't physically move, you didn't take a path, you teleported, right? Now that doesn't happen for large objects, but for electrons, that's happening all the time around the atom, okay? When you're not peeking at it though, it's actually, and this is even weirder, I think, it's actually in all this whole space. It's that electron is everywhere in that space, and there's an infinite number of possible spots it could be in there, okay? But it's everywhere in there. And then when you peek, it becomes one spot, okay? So this act of observing and peeking at it has an effect. Remember, even like focusing your conscious mind seems to have an effect on these experiments, which is very, very strange. I think really cool and fun, but anyway, kind of strange. Now I'm going to tell you that like the double slit experiment where they tried to alter it with their mind, the effect was weak, but statistically significant. So if you have a statistically significant effect, okay, like they were able to reduce the interference pattern by just a small percentage, okay, barely perceptible, but the computer perceived the difference every time. And that, you have to explain that. If you can repeat a result like that and have repeatable, statistically significant data, science demands an explanation, right? We don't have one, but it demands one, you know, when you think about it. All right, so now that we've seen this, let's go back to this. How do you explain all this? Well, we don't have very good explanation. I'm going to warn you right now, none of these are testable, okay? Einstein hated this part of quantum physics, just so you know, even though he came up with the photoelectric effect and everything, one of the founding fathers of quantum mechanics. He didn't like this probability thing, where like there seems to be random chance involved. Like, so like if I peek at where the electron is and poof, it shows up somewhere, but it seems like there's a random element, like you can't 100% predict. He thought that there must be a normal explanation for all this, forget the teleportation and everything else. And he famously said, you know, God does not throw dice. And Niels Bohr, who came up with the stationary states, like the energy levels in the atom, said, stop telling God what to do. That's what that was a response to Einstein. Okay, so anyway, uncertainty principle. Okay, Heisenberg came up with this thing called the uncertainty principle. So like I was telling you, the object's position is uncertain, which doesn't mean that we just don't know where it is. That's totally wrong to think of it that way. What you have to think of it as, its position is in more than one place at the same time. So it's in many places simultaneously. And that's what we mean by uncertain. It's actually a physical property of matter, that the position of the particles, it's not one fixed position, like it's like in many positions at once, okay? Now I went through this, which we're not going to do because we don't have time. I went through this energy and time uncertainty and position and momentum uncertainty. So this is Heisenberg's uncertainty principle. There's no problems on this in the textbook, so I'm just going to skip this for now. Energy and time is really cool. Like you can get over brief periods of time energy that just shows up out of nowhere, and that violates the law of conservation of energy. Like these things are violating what we thought were physical laws all the time, but they're doing it on such tiny scales that we don't notice it, okay? And on big scales with big objects, these effects kind of cancel out, and we don't get any weird quantum effects, unfortunately, because it'd be kind of cool for large objects. Okay, I talked about pair production. Had we done like radioactivity, you would have read about this already, but we didn't do the independent unit. And so, yeah, you can get like a photon, which is a particle of light, turning into particles of matter. Okay, so that's using Einstein's like mass energy equivalence. And this energy can come from nowhere. Like you can literally have nothing, just a vacuum outer space. And then all of a sudden, two particles show up. And they always come in pairs, matter and antimatter particle. It's sort of completely random event. Okay. Now there's different ways of interpreting this wave-particle duality thing. The Copenhagen interpretation is like, it's like we're not even going to bother to try. We're just, look, we have, let's say we're talking about light. Well, we have the wave model of light and we have the quantum model for light. When we're doing certain experiments, we'll use quantum. When we're doing other experiments, we'll use waves. And then we've got it all covered, right? And then it's like sort of like, well, who cares about all this weird stuff? Like you can't marry these two theories together. Well, it's kind of important, I think. It's sort of like not, what we're going to say is, listen, guys, let's not go there. Okay, let's just make measurements and make calculations and build devices and stuff like that. But let's not try to explain things. But I think that's one of the goals of science. And I think, like, if you're an engineer, you just want to build a device that, a laser or something like that. Okay, well, knock yourself out, right? But if you want to explain the fundamental concept, right, of what physically something is, then the Copenhagen interpretation is not your answer, okay? Then there's this many worlds interpretation. So if you've watched The Flash, or there used to be the show called Sliders years ago, you will probably not have heard of it, where they used to slip from one Earth to another Earth, and there's like an infinite number of Earths. Okay, last year on The Flash, they had Crisis on Infinite Earths. So there's like a version of Superman on all kinds of different Earths, except not this one, right? In this Earth, Superman is just a fictional character, but on some other Earth, maybe he's not, right? And so, anyway, they have how do we come up with this weird thing? Well, think of it like this. Maybe, how do you explain how the electron is in many places at once? Well, maybe it really is in many places at once, just in alternate universes. If many worlds interpretation is true, there'd be many different versions of you, all in this infinite sort of multiverse, okay, where, like different things have happened to different versions of you in these different universes, okay? Actually, I've got to change this. This is referring to students that graduated a couple of years ago. Anyway, hidden variables. This is one that Einstein liked. Einstein liked to say, well, maybe things aren't really bizarre. We just don't have a good explanation for what's going on here, but there is a sort of logical explanation for what's going on. You can explain everything using sort of classical physics like Newtonian mechanics and Einstein's theory of relativity to account for everything. But we just have to know what all the variables are. So there's some hidden variables that are making things appear strange and confusing, but they're not really truly random like it says. Well, yeah, it turns out that Einstein, like all the experiments that we've done in quantum physics since, have sort of proven this idea more or less incorrect, okay? I should talk to you about the cat before we sort of leave all this, Schrodinger's cat. So Erwin Schrödinger he talked about the cat, right? And the cat in the box. And what you do is you tie the life of a cat to a quantum event. Okay, so if you want to try to understand what's going on, let's say you have a radioactive particle and you put it in the cat, put the cat and the particle in a box, and then when you open the box to observe the radioactive particle, you'll find it's either decayed or not decayed. But what quantum physics is saying is when the box is closed and no one's observing it, okay, the particle is both of those things at the same time, okay? And then when you open the box and observe it, all of a sudden it collapses down to one thing, okay? And by putting the cat in the box and you put a vial of poison in there so that if the particle decays, it kills the cat, whatever. Now you've tied the life of the cat to it. So the cat then is both alive and dead before you open the box. And you're thinking that's not true, it's just wrong. You're speaking nonsense. But the thing is by showing you the cat example, it shows you how weird it really is. So if you don't appreciate how weird it is, if you're not thinking it's nonsense until you heard the cat story, something's wrong. Because it is weird, and it's as weird as a cat being both alive and dead before you open a box and observe it. Okay. All right. So one last thing, and then this will finish off our unit. This is sort of unrelated to the quantum thing, but in the early 20th century, so in the 1900s, they built particle accelerators. Okay. And particle accelerators and pair production and everything else, you crank up the energy and you see what happens. And what happens is by the early 20th century, so the early 1900s, when Einstein was around, they knew about protons, neutrons, and electrons, right? These are all matter particles. And they knew about photons, which are particles of light, so we've been talking about that, of course. Then they invented these particle accelerators where they could increase the energy density inside these machines to much higher levels than would exist naturally in the universe, okay? And what happens is you get pair production. In other words, energy turns into matter through a random quantum event, and then these other particles will show up, right? Now, sometimes you get an electron, sometimes maybe you could get a proton even, okay, or a neutron. In fact, I don't think they ever got anything that big, but anyway, what happened was they, when they were looking at the particle accelerators, they found particles that showed up that no one had ever seen before. And we never knew existed. Like, in other words, like everywhere you look in the universe, all we see are protons, neutrons, and electrons. That's all we see and makes up everything we see. And then if you get the energy density high enough, all of a sudden this other particle showed up. And the first one, they named it a muon, okay? And it had the same mass of an electron, but it was hundreds of times more massive, like 200 times more massive, okay? And the scientists sort of famously quipped, like, what? Like, who ordered that? Like, where did that come from? And they repeated the experiment. It showed up many times, and they were like, what is this? Anyway, since then, they increased the energy even more and discovered a whole host of particles. Okay, one of them was called a quark. Turns out that protons and neutrons are not elementary, but they're made up of other types of particles called quarks. Okay, so a proton is 2 up quarks and 1 down quark. And quarks come in several colors, like red, green, and blue. Okay, and so on. Anyway, I've made a table here. I didn't make it. I found this table online. That sort of summarizes everything they found. Okay, and I'm just going to circle a couple things. Everything in the known universe that we see is just made up of these 4 guys. Okay, these 2 guys make up protons. I'm sorry, I'm not writing very well. And neutrons. Okay, electron you know very well, so we can check that one off. You know where that goes. And electron neutrinos we see in nuclear reactions. Okay, so in other words, like when there's a radioactive decay, sometimes you get a neutrino that's released. It's a very tiny, it's called little one, the little neutral one. Now we call it the electron neutrino because this first family we'll call the electron family. Okay, family number 1, the Roman numeral number 1 at the top. Now, the muon was the first weird particle or exotic particle that they discovered, right, in the particle accelerator. And its mass is much greater, like 200 times more massive than the electron. It has the same charge though, negative 1.602 times 10 to the negative 19 coulombs, right? So it's like a big brother to the electron, it's just bigger, okay? Anyway, they later discovered the tau particle, which is sort of the mother of all leptons. These guys here are called leptons because they all have the same charge, negative 1.602 times 10 to the negative 19 coulombs. So the tau particle is over 1,000 times more massive than the electron. So it's huge. This huge, called a superparticle, right? It's this gigantic particle, but it's like similar to an electron in every way, has the same spin and the same charge and so on, but it's absolutely huge. And then each one has a corresponding neutrino. Okay, so here are the 3 neutrinos here at the bottom. Okay, now these particles are neutral and have a smaller mass, but the muon neutrino and the tau neutrino are much, much larger than the electron neutrino. Okay, now at the top, you will see the various types of quarks here highlighted in purple. So the first quark that they discovered besides the up and down quarks was the strange quark. Now you can imagine how they named it, right? It showed up in the particle accelerator. Well, that's strange. Okay, so there you go, Mr. Scientist. That's a good name. Let's call it the strange quark. And charm has a sort of same sort of quality to it, right? Like charm meaning like almost magical. Like where did this come from? Okay, so charm and strange quarks, and then top and bottom quarks. The top quark is the heaviest known particle of them all. Okay, So the quarks are heavier than the leptons, so the green guys down here, and the top quark is by far the heaviest of all quarks. Okay, you can see by its energy how heavy it is. Okay, so it has a very high energy there. It says 172.44. This one here is 4.18, and here 95, 1.275, 2.4, and 4.8. Like, that top quark is enormous. Okay, now the look how you can look at these guys too. Notice how it's giga electron volts, giga here, giga compared to mega. Giga is 1,000 times more. So think about that for a second, how much bigger these things are. And these are all the force particles that they've discovered. Gluon for the strong force, right? Photon for the electromagnetic force. These ones are for radioactivity. Okay, and this one has to do with mass, Higgs boson, okay, which they have recently experimentally confirmed its existence in a particle accelerator. Okay, now we think that there may be space for one more for gravity called the graviton. We already have a name for it, but we've been unable to confirm the existence of such a particle, so it does not make it to the list. We call this basically the standard model. Like, this is where these are all the particles we've discovered. Okay, but all the ones that for us, I'll highlight them here, these are the only ones you see in everything around you all the time. Okay, the energy levels in the universe are not high enough for stable versions of any of the other particles on this table, except for the force particles, okay, like the photon and gluon and stuff like that. Okay, so anyway, I put this in here, baryons, mesons, like there's different names. Like, these guys are, the leptons are the green ones, the quarks are the purple ones here, and then the bosons are the force carrying particles. But we have other names too. Hadrons are any particles that consist of two or more quarks. So for example, a proton or neutron are an example of hadrons. But if they have three quarks, which protons and neutrons have, we call them subclass baryons. So baryons, proton and neutron are the most famous baryons, right? Okay, a proton is two up quarks and a down quark. A neutron is two down quarks and one up quark. And these things can transmute themselves. So a proton can turn into a neutron and vice versa. And that's in the process of radioactive decay. Now, are there more particles that we have yet to discover? Well, we're not 100% sure. We had no idea these ones would show up, right? No one theorized that these would show up. We just found them. No one could have guessed that these things exist at all. But there are some theories out there that say that we should find more. So, for example, there's a theory called string theory. String theory says that all of these particles are just manifestations of harmonic modes in these tiny vibrating strings. Okay, and if we can get the energy higher, these strings will vibrate in higher modes and we'll get even larger superparticles. Okay. So anyway, that's it, guys. That's the whole course, and I wanted to finish it off in one lesson. And so today there's not much math to discuss. Okay, it's just talking about some weird things, some weirdness, and like how we wave particle duality and stuff like that. I want to just show you in the outline where we are. Okay, so like there's no homework here, of course, so you can forget that. Here, this homework here with the fermions, so I made the table for you. It's in your notes, so they can check that one off. Here, let me use a different color. Like here, we can check it off. There are 48 fermions. The reason why the table seems to be missing some is that each quark, so I'm doing some of this for you, comes in 3 colors. Red, green, and blue. So if you look at that table with the quarks, the particle zoo, okay, there are 6 quarks here, times 3 is 18, right? Because each one comes, like there's up quark, red, green, blue, down quark, red, green, blue, right? There's 3 of each of these quarks, so that makes 6 times 3 is 18. But then each particle here that has mass has a corresponding antimatter partner, right? So if there's 18 quarks that in the matter universe, there's also 18 antimatter quarks. So that makes a total of 36 quarks. Now, the same thing, the leptons do not come in different colors. So there's one electron, one muon, one tau, and then the neutrinos, same. But then they come with antimatter partners, so there are 12 leptons, 6 here, and then 6 antimatter. Like the positron would be an antimatter electron, and so on. It's not listed on this table. So the antimatter ones aren't listed here. So that makes this 12 and that 36. So all the particles that have mass, they're called fermions, total of 48, 36 plus 12, right? So if you go here, also the antimatter twins are not counted. So that gives a total of 48, okay? GUT is grand unified theory that attempts to merge what we call quantum physics with field theory, like for example, electromagnetic wave model and universal gravitation and sort of the Einstein's theory of relativity with quantum theory, okay? TOE is a theory of everything. String theory tries to do that, including come up with how gravity works. Higgs boson gives particles mass, okay? And a string is this little bit of stuff that makes up everything in the universe, right? Okay, so it's a fundamental. It's a fundamental bit of matter, if you like, energy. Okay, you don't really need to know that anyway. So, like I said, we're not doing radioactivity and radioactive dating. We did it last semester. You guys are off the hook. So that's it for the course. Yeah, I mean, I know I kind of went through it quickly today, and it's been a 45-minute thing, but that's it, guys. I'm going to post a practice test for you. We're not going to do radioactivity. This test will be mostly multiple choice, and since it's open book, it's pretty, I think, pretty easy. But anyway, very little homework in this section, only those questions up here at the top. And my practice test for you, you'll see what I mean, okay? And that will finish things off. And we said that'll be Tuesday next week. So it's Thursday today. That gives you 4 days to get ready for this. Okay, and I can update your marks up to Tuesday night, and I will. So whatever your final mark is at the time, I will give you either the mark you have now or the mark you have pre-pandemic, whatever's higher. Okay, yeah, and that's it. So guys, take this opportunity. You can do well on this. Don't throw in the towel now. Like, you guys have been honestly my best class. Okay, and I was feeling really sad and disappointed yesterday with the whining and complaining on the group chat. I get it, you want to be finished, I want to be finished too. We are almost finished. Okay, there's very little left. Okay, and I'm not going to make this test like a killer test or anything. You'll see the practice test, you write the test, it'll be basically the same. Okay, so let's finish it off. There's no final exam, of course, no CPT or anything like that for me. Okay, so we're just going to get this done, and then you can relax and enjoy your summer, okay, and get ready for university and everything. All right, so I'm going to sign off for now, and we will talk again soon.